In this section, we're going to make a leap into another form using the integral idea. But let me back up a little bit and set the stage for this. When we talked about derivative, when we say the word derivative, we could think of two different ideas. We can think about the derivative function, or we can think about the derivative at a point, the derivative of a function at a point. And the interpretation of the derivative at a point is slope of the tangent line at that point, or it is rate of change at that point. You see, so, and we have a similar idea when it comes to integration. That is, we can talk about an integral function and we can talk about a definite integral. And that's what we want to get into right now, is the idea of a definite integral and the interpretation that we make for that integral. Let's go through that. The interpretation is area under the curve. It's a really interesting idea, and it's a rather powerful one as well. But consider that we have a function here, and consider that we'd like to find the area that is between the curve and the x-axis and within a particular interval. Now that's what integral, a definite integral is all about. It is the area, and the notation for it is, now notice the integral notation here, but we have an a and a b. And this is the lower limit of integration, and this is called the upper limit of integration. And that's all there is to it. So this is our interpretation then for a definite integral. Now this doesn't say anything about how to calculate it, but the method of calculation is given by a rather auspicious sounding theorem. It says the fundamental theorem of calculus. Wow. And it is this, that we find this definite integral by making a simple calculation of f of b minus f of a. Now notice the uppercase F here and the uppercase F here. This just means that we are evaluating within the integral function. You see, this is the integral function associated with that lowercase f. So it's uppercase F of b minus uppercase F of a. Now just realize, and I'm sure you do right here, that this relationship between the lowercase f and the uppercase f is that the integral of the lowercase f is uppercase f, and that the derivative of this rascal is equal to the lowercase f. So that's the idea. Now, in your textbook, you have a list of properties. We're going to encounter them. They're rather intuitive. I invite you to have a look at them in your textbook. But let's go through and use the fundamental theorem of calculus to make a calculation involving definite integral. Consider this function and consider this domain. Now, from 1 to 2, if we're going to construct the graph here, and often we'll be doing this, we'll kind of look at that visual or geometric interpretation of the situation. We'll have some business interpretations involved with that as well in just a little bit, but for right now it's just area under the curve. Now in the interval from 1 to 2, and here's our graph, but in that interval you see we have this, and we're calculating with this definite integral within this interval, we are calculating this area. The notation for it is the integral from 1 to 2 of our function dx. All right, that's all there is to it. Now, how do we go about making the calculation and using a particular form for uppercase f of b minus uppercase f of a? How do we do that? Well, we're going to do it this way. Let's slide over here. Here's the form. Now, here's what we're doing. This is our notation for the process of definite integration. And here's another notation that we're going to end up using. We're going to say, well, gee, part of the process is to find the integral function. So let's find the integral function and then somehow indicate that we are going to evaluate this within a certain interval. And the evaluation indicator is over here, this bracket business, lower limit of integration, upper limit of integration, and then we go through the f of b minus f of a business. So let's use this form on this problem. So here we go. We have this. Now we find the integral function associated with this, and here's that integral function. And now we use this notation about the interval in which we're finding this area. All right, and then it's the f of b minus f of a. Now here's the f, the big F, and it's f evaluated at b. See, so we replace within this, we replace x with 2 in both places, and then minus, and then the f of a is the f of 1, you see, and so replace these x's with 1, and then evaluate, and that's all there is to it. Now, if you keep things really organized here, it's not a very big deal. This is not a big stretch from what we have been doing before, but I encourage you to write a step. This step is really important because the tendency here and the temptation, I guess, is to try to perform operations as you go, to try to anticipate what's coming. Don't do that. Just to consider this almost like a formula where you're just plugging into a formula. Not performing any operations, all you're doing is replacing within this expression, you see, for the upper and lower limits. So bam, just replace within here for the x's, and then minus, replace within here for the x's, the lower limit, and then away you go with the evaluation process. All right, so it turns out that 4/3 then would be the area indicated here with the stripes. Let's go through another one. We have the definite integral from 0 to 1 of this function. Now notice it's a binomial squared, and it's in terms of t. And now we go through and we're thinking through this. Gee, this is what kind of form is this? We're thinking of the integral function at this point. We need to find that integral function first, and then we are going to evaluate it at the various limits of our integration. So let's see. We have this u squared idea, and we need a u prime. Oh, the u prime would be 4, so we need a 4 over here to meet the form, and we create that by putting 4 here and 1/4 out here. Okay, now we have the u prime form, and now we know how to go through the integral process, or the process of finding the integral function. And so we do that, and it turns out to be this, and then our indicator for our limits of integration are indicated over here, and away we go with this f of b minus f of a. Now this part is the f of b, and this is the f of a, just for emphasis here. So here's the f function that I'm talking about here, the uppercase f. And within this we are replacing the t with 1. You see, this t is replaced with 1, and everything else just comes down as we see it. And over here, we're replacing t with the 0, you see, and everything else comes down. And now we evaluate. I'm not going to go through every little step in the evaluation process. I think we can see through that rather easily. It turns out that the area under this curve, or between the curve and the x-axis and within the interval, is 31/3. Here's another one. And all of this, I think, is a matter of organization. If you have good organizational skills, you're not going to have any trouble with this. It's the integral from 0 to 3 of e to the 2x dx. And now we have to change our thinking. We have so many integration forms here that we have to keep track of. And as you go through homework and so forth, you might have a list of those forms close at hand, so that you can refer to them. And the form that we're looking for here, and as you think through it, gee, we know that the form that we use for integration for e to the u is e to the u times u prime. So we have this u prime notion, and the integral is e to the u. Well, gee, we have to create this form within that expression, just like we did before. I mean, there's no difference here. The complication and the thing that seems difficult here is that we're introducing the notion of definite integration, but part of that process is exactly what we did before, and that part is finding that integral function. All right, so to create this u prime situation, well, here's the u prime then would be 2, so we need a 2 factor over here somewhere. You see, and if we're going to introduce a 2 factor here, we just put a 1/2 out here, and that's what I'm doing in the next step. Now notice that I put the 2 factor on the left. It could have been placed at the right. Doesn't make any difference. So we have 2, the 1/2, you see, to offset one another. Now we have the form we need in order to integrate, and so the integral function is e to the 2x. And now we have our limits of 0 to 3, and away we go with the evaluation, the f of b minus f of a business. So we have the x is replaced with 3 in this one, the x is replaced with 0 for this part. And away we go. Now notice that this is e to the 0, which is 1, and this is e to the 6, so e to the 6 minus 1. And evaluating this using the calculator, presumably, we get approximately 201.21. Here's one more. Same idea in the sense that we're following the same form. Different idea in terms of finding the integral function, just a little bit different. So we have the negative 3. Now if we have a coefficient here like this, we can slide that coefficient to the outside as we have seen in the past and express the square root of x as x to the 1/2 power. And then it's pretty easy. The integral here becomes x to the 3/2 over 3/2. And now we just tack on our limits of integration, you see. And then go through the evaluation process. The f of b means take this expression and replace x with 4. You see, and then the minus the f of a part. Here's the f of a part. It is take the integral function and replace x with the 1. And then we go through the evaluation process and we find the value to be negative 14. I do want you to notice that a definite integral like this could be a number which is positive, a number which is negative, or a number which is 0. And any of those would be appropriate. Even though we often think of area as being positive, we might think of an area below the x-axis in a different way. And we'll have a chance to look at that in a little bit. But you might take a look at the graph of this and the interval over which this occurs and see how this interpretation of negative 14 comes about. You may have noticed that one of the properties looks a little peculiar, and it is the property that has to do with sort of splitting an integral. That is, if we want to take a definite integral, then we can actually split the interval over which we take it. That is, we can take the integral over part of the interval and then the integral over the other part and add them together for the overall integral. And you might be thinking, gee, when would we ever use that one? Well, we're going to use it in this next problem. The problem involves an absolute value function, and it's the nature of how we're going to interpret this function that gives us the two pieces involved. Let's first, though, interpret what we have here. It's the integral from 0 to 2 of this function. And here's the graph of the function, and the integral refers to area under the curve. And the area under the curve then from 0 to 2 would be this little area, and also the area over here up to 2. So we're calculating the area of this little part with this little part. So it's those two together. Now, here's why it splits into two cases. The absolute value of this expression will be the expression itself as long as the value of the expression is positive. You see, now when is the value of the expression positive? Well, it's positive for x values that are greater than or equal to 1/2. You see, if x is 1/2, we have 1/2 times 2, then minus 1. And when x is greater than or equal to that, we have the absolute value of the expression is itself. So the definition of this splits into two cases. One case is that the absolute value of the expression is the expression itself as long as x is greater than or equal to 1/2. But if x is less than 1/2, then the expression itself becomes negative. Absolute value then means we want the opposite of this expression. So we define this then as being the opposite of the expression when x is less than 1/2. All right, now we have split into these two cases, and that's why we need to use two parts in this integral idea. So the integral of the function on the interval from 0 to 2 is equal to the integral from 0 to 1/2 of this function, you see, plus the integral from 1/2 to 2 of this other function, this other expression. All right, and away we go. We just kind of follow our nose through it from here the way that we would expect. Now, the integral function associated with this is negative x squared plus x. And I'm confident that we can do that part. I don't want to get into the mechanics of that right here. We have other fish to fry. And let's see, so this is the uppercase f function that we talked about before, and the interval is from 0 to 1/2. Then slide over here. The uppercase f function associated with this, the integral function, is x squared minus x. The interval is from 1/2 to 2. All right, and then back over here. Now, it's this transition from this step to this step that is so critical in getting a problem like this correct, because it brings to bear all of the organizational skills that we can come up with. Now remember, it is, for this part, it is f of b minus f of a, and the f of b means uppercase f of 1/2. Well, that means replace these x's with 1/2. You see, and then for the other part, it's minus f of the a. Well, the a is 0. So the f of a would be the replace these x's with zeros, you see. Now, notice the use of parentheses here, and we'll go through the other part in just a second, but the use of parentheses, particularly right in here, this is the negative of x squared, and this minus sign is not part of that squaring process. This doesn't mean we have 2 factors of negative x. It means it's the negative of 2 factors of x. And we want to emphasize that. We want to make sure we don't make the mistake of plugging in the 1/2 here and squaring negative 1/2. We are squaring 1/2, and it's the negative of the 1/4 that we're talking about here. All right, so that's why the introduction of extra parentheses here to emphasize that idea. Now over on this part, so here we have, let's see, the f of b minus f of a. It's f of b, that's f of 2. Replace the x's with 2. You see, now notice that all of these are blind replacements. We're not performing any operations. We're just blindly replacing these x's with 2's and bringing down the expression. And then the minus f of b means f of the 1/2. So replace the x's with 1/2. You see, and away we go. All right, when the smoke clears on this calculation, we find the area, that total area under the curve, to be 5/2. This next problem involves a marginal idea. Remember, we talked before about marginal profit and marginal revenue and marginal cost, and that just had to do with the rate of change in profit, rate of change in revenue, rate of change in cost. And here we're given a marginal profit function. And notice that I'm emphasizing that this is a derivative idea because this expression is the derivative of profit with respect to x. So it's the derivative of something. And in this problem, we're going to be asked to find the integral. Where did this come from? You see, that's the idea. We want to find the change in profit when sales increase from 100 to 110 units. Now, we know the rate of change in profit is up here, but what about the amount of change in profit when sales changed from 100 to 110 units? Well, that's an integral idea. So it's the integral from 100 to 110 of this marginal profit expression, you see, or function. So away we go, and we just kind of follow our nose through it the way that we learned before. The integral function here is this expression, and we're evaluating from 100 to 110. So f of the b would means to replace these x's with 110. You see, write the same expression, replace the x's with 110, minus f of 100, replace these x's with 100, and perform the indicated operations, and we find that change in profit to be $121.48. Here's a problem or a situation involving average value. We actually are going to have something that's related to a formula to calculate average value. Let's think about what average value means. It's the average value of a function on a particular interval. Now, let's look at it graphically first. Let's say that this is the graph of the function. Its average value. Now, the value of the function at a would be this distance, this vertical distance. You see, this y value is the value of the function at a, and the value of the function at b is this vertical distance. So what is the average value? Well, the average value is, let's see, some vertical distance that's between these two, more or less. And so it would be something like this value. So it is a value which is y equals that value. All right, so that's the idea. Now we find that average value of the function within the interval like this. It's 1 over b minus a. Now notice the a and b are the endpoints of the interval. So it's 1 over b minus a times the integral from a to b of the function. Now the derivation of this, how this was derived and how we come up with this, is not for us to have a big discussion about. It's a little bit too involved for us right now. But let's just use this almost like a formula to find the average value in a particular situation. Suppose we have a cost function. Now this is cost in terms of time, and this is the cost per unit in terms of time. T is time in months, and time runs from 0 to 24 months, so this is time over a 2-year period. Now, the average cost per unit during this time period is what we want to calculate. So, average cost, the average value of the function then in this interval from 0 to 24. So, it's using this relationship and just plugging into it like a formula. Away we go. We have 1 over, let's see, b minus a, 24 minus 0. And the interval is from 0 to 24. And our function is this cost function. Now we want the integral function of that cost function, and we've calculated it here. And we have 0 to 24 as our interval. So once again, we just find f of b minus f of a, the f of b. Replace all these t's with 24 for this expression. And then minus f of a. Well, f of a means replace these t's with zeros. All of these terms go out, so the expression just becomes 0. And then performing the indicated operations, we find that the average cost per unit in that interval of time is $14.23. Now, what have we actually calculated here? Now remember, if we look at it graphically, it's kind of like this. And by the way, I'm noticing that this cost function is quadratic, so it has a single curve involved in it. And I don't know exactly how that curve goes. Maybe it goes something like this, though, let's say. The cost is just increasing maybe over that period of time. So here is time and here is cost, and maybe this would be 0. 24 might be about right here. So the average cost might be in this neighborhood. You know, somebody owning this business might want to know exactly the point in time when that occurs. When does this occur? Okay, we know what the average cost is, but when does it occur over that interval? This should be a horizontal line. Let me draw it that way, if I can. Let's see. There we go. Somebody might want to know, gee, where along this time interval does this average cost occur? Well, we can find out just by taking that average cost that we calculated down here, $14.23, and pop it right back in here. Replace the c with 1423 and then solve this for t. It's a quadratic relationship, so we subtract 1423 on both sides, and that'll impact the constant over there. Then we have a quadratic equation. We can pop the information into the quadratic formula and easily solve for t. You may have noticed that techniques for integration can become rather involved, and any little advantage that we can gain here and there might be helpful. And we can gain such an advantage if we can recognize even and odd functions under particular circumstances. Now, you studied even and odd functions in pre-calculus, and let me refresh your memory. Even functions had the characteristic that for every point on f of x, you have a point f of negative x. So f of x is equal to f of negative x. And all that means is that the function is symmetric to the y-axis, or the graph is symmetric to the y-axis. Now, if we are taking the integral along an interval which is split by the y-axis, then notice that what happens to this area. We have the same area over here as that we have over here. So really, in making the calculation, all we need to do is find this area and double it for the integral over the entire interval. Now, this doesn't seem like a great advantage, but it does come in handy in certain situations. In other words, here's the idea, that if we want to take the integral from negative a to a of f of x, then all we need to do is double the integral from 0 to a of f of x. All right, so that's the idea with even functions. Now with odd functions, the advantage is even greater, because now odd functions had the characteristic that they were symmetric about the origin rather than symmetric about just the x-axis. Now the origin goes through, the origin is right here. Okay. And if you recall the discussion about that, you took a point on the function over here, and if you go through a double fold idea, then that point ends up making its appearance down here on the graph. So f of negative x is equal to the negative of f of x, and that was a relationship that you investigated to verify that you had an odd function. Now odd functions, some of the main ones that you studied were third degree polynomial functions. Particular ones of those, not every third degree polynomial function, but certain ones of those that went through their origin, for example, many of those have this characteristic. At any rate, here's the idea, that because we have an area, if we're talking about, again, an interval that kind of is split by the y-axis, from negative a to a, the integral described here is a negative number, and the integral over here is a positive number. And these areas are the same above and below the x-axis, and therefore they'll take one another out. So the integral from negative a to a of f of x dx, if f is an odd function, that this becomes 0. Now how is all this helpful? Well, take a look at this situation. We have the integral from negative 4 of this great big polynomial function. Now, integrating here is not a real big problem, but look at how easy it is if we can recognize even and odd parts. That is, we can separate this expression into even and odd parts. This x cubed minus 2x. Once you become familiar with this, you realize that this expression represents an odd function. And the leftover expression, the 6x squared minus 3, represents an even function. So we can utilize these characteristics over here. Because this is an odd function, and we're splitting, you see, we're splitting our interval with the y-axis, so this simply becomes 0. And this becomes double the interval from 0 to 4. Now there's some advantage there because of this 0 as the lower limit of integration. A lot of times this will go out or become incredibly simple under these situations. And here we go. We have double. Now the integral function is 6x cubed over 3 minus 3x, and 3 and the 6 cancel, leaving 2. So now notice that we are integrating 4 to 0 here, or f of 4, replace x with 4, f of 0, replace the x's with 0. Gee, both terms go out. You see how easy it becomes under these circumstances, and then evaluating here, we find the integral to be 232.